All right, and hello everybody. I'm glad you're here. We have been talking about the strength of the robot hand. And we had this robot that's standing here. This one has his feet or her feet on the ground. And then we asked the robot to move into a configuration where the robot is not on the ground and the whole weight of the robot is being held up by the hand. And it was just a graphic way to demonstrate and show the strength of the hand. And I realized that a lot of my robot discussion is what I call hydraulic cylinders, the use of hydraulic cylinders to make a robot that moves around. And these hydraulic cylinders are causing the motions of the robot to occur. And I realize that I've been talking about that, but I don't know that I've ever really shown how that works in a robot, a hydraulic cylinder robot. I decided to call it the piston robot because hydraulic cylinder robot is just too many words. So I think I'm going to take a sort of a break from the absolute discussion of the strength of the hand to just show you how I got this robot from here to there. And that will let you see how hydraulic cylinders work and how well they work and how nicely they allow you to have a human mimicking robot. And of course, we always want to start. This is in Keyshot. Hello and welcome. I am glad you're here. I do have a YouTube channel named Patrick Gray. I invite you to subscribe. I think you'll enjoy it. I have a website. There's pages. One of the pages on the website is Give the Robot a Hand. And all of this hand discussion will be there. I also try to create YouTubes and send it to YouTube. And again, we do have a robot that's moving, and those limbs can act like scissors with hydraulic force and hurt somebody. But the truth is, any physically real object could potentially hurt somebody. And so if you're managing a physically real object, I advise that you should manage it in a manner that is legally allowed and reasonable and safe. And if you can't manage it that way, it's my advice, do not create it as a physically real item. And the other thing we like to do is just see what is here. A beautiful sky. This is Microsoft Bing wallpaper, bathing huts. Well, hopefully the water's not too cold, but I see this as construction of the hydraulic cylinder, how to obtain sensory information from the hydraulic cylinder, how to make a valve that moves the hydraulic cylinder, how to put together the programming that allows the robot to stay balanced, etc., etc. And each of these is important and needs to be discussed, and they really are almost completely separate topics. And I'm talking today about moving the hydraulic cylinders around, or at least the pistons around, to move the robot. And I could do this in a very fast way, but what I've found happens if you're moving too quickly, either you leave stuff out and people don't understand what happened, or if you're going fast enough, things happen that nobody notices and it becomes confusing. And when they say, well, how did he do that? And the answer is, I don't know how he did that. So I'm not going to go that fast. I like to keep them at 15 minutes so I can put them on LinkedIn. So when the time gets to 15 minutes, I'll just stop and we'll go in and start a new one. And so we'll say goodbye to the little huts of robot function. And we do have them down here. That's the same setup. And I want to discuss this in SketchUp, because SketchUp, for me, makes moving things around easier. SketchUp is also it's called cartoon or tune mode. It's optimized so that everything is easy to see. All the corners are sharp. All the lighting is perfect. There's no shadows where you can't see anything. And there's ways of moving stuff around that is very easy in SketchUp. And so that's what I'm going to do. And we're going to move the robot. And remember now, just like a human being, this is a human mimicking robot. And so it can have all sorts of forms and configurations, and we're just going to pick the one that we pick because I'm showing you how this works. And so we're starting out with the robot. It is a little bit standing with its feet behind these bars, or behind the supports of these bars, because it's just standing there. It's leaning forward a little bit, and it's got its hand up here on the bar. And we're going to begin the process of saying, okay, lift yourself up and get your feet off the ground. It's important, I think, to mention that these materials are alloy stainless steel, 2205 alloy stainless steel. That's 2.7 inches across. And if I remember correctly, it's, yeah, 1/8 of an inch thick. That is immensely strong. So all sorts of forces can be put on this metal, and nothing is going to happen. If this robot weighs 200 pounds, I don't have a biceps yet. I haven't finished the forearm. But let's just look at how strong is this. And a problem of SketchUp is you have to get to this individual part, which takes time. So I'm going to put it on pause. And I have navigated down to this exact part, and we can isolate that. And we can look at the cross-sectional area, and it's 0.6204 square inches. So the tensile strength of this is 40,000 pounds, and the compressive strength for it is 20,000 pounds. What does that mean? The simple truth of what it means is basically we can do anything we want to with this robot and its hydraulic cylinders. Nothing is going to break, and we don't have to worry about the forces. They're not going to do anything that would damage the robot. And that's the point that I've been trying to make. And that's why it's designed the way it's designed. And that's why it looks a little bit complicated, is because all of the designs that were available, I only picked the ones that allow dramatic strength to the robot. And in addition, every joint has the same range of motion as a human joint. Every joint is located where they are in a human, and all the proportions are the same as a human. So this is a human mimicking robot. And a concept I want to put out here is what I call the committee of 12 spouses, or 12 significant others. This is a human mimicking robot. So when we want to decide, well, what is this robot going to do? We don't need a PhD in mechanical engineering. We don't need a PhD in robotics. We don't need a PhD in computer programming. We just need a human being. Compared to what robots can do, normal human beings are absolute Svengali level perfection experts on human motion. And so if you want to know what a human mimicking robot should do or could do, you just ask a regular human, well, if you were there, what would you do? It's as simple as that. And this is only true of a human mimicking robot that meets all these criteria. It has so much strength that it's not going to damage itself. It has all the joints of a human being. It has all the ranges of motions of all the joints. It has all the axes of motions of a human, and it's all put together as a human. So if you want to say what can it do, and someone gives you an answer of a motion that is what a human can do, you don't have to say, yeah, well, our robot can't do that, because he can or she can, because it's a true and absolute human mimicking robot. So the first thing we'll ask our committee of 12, and why did we pick 12 spouses? Well, I mean, the spouses of the people who work in the robot lab are just regular people, or their significant other. It's like, well, what's the first thing that's going to happen when this robot gets its feet off the ground? And you know, you have 12 people, you'll get 12 answers. But my suggestion, I'm going to push this a little bit, is I think the first thing that's going to happen is the robot is going to open up this shoulder and abduct the arm. And it also allows me to show you how we can abduct the arm. So that's the first thing we're going to do. And all of these motions that we're doing, they do them one by one because you have to in SketchUp as a drawing program. Remembering this robot is free. I didn't pay for it. Nobody created it. In exchange for it being free, we have to move it around inside of a 3D drawing program. But I would much rather create a 3D drawing program of this robot and optimize it instead of creating it, realizing it didn't work, tearing it all apart, and paying money to create another one. So that's why it's inside a 3D drawing program, and why we have to go step by step. And which particular step we pick first, I'm not sure it's that important, other than we have to go step by step. So we have to pick one. And the one I picked to start with is abduction of the shoulder. I do want to mention she does have a big clock. It's run on batteries. It's about 12 inches in diameter, and when I start running out of time, she'll hold it up, and that means I've got to stop talking. And so what we'll do is we'll close out the video and then just start another one. And we're going to see, I think I have time to get down to how are we going to open up this shoulder to abduct it. And we have to take in SketchUp and start moving down into the groups, and that takes time, but I'm going to pause it while I do that. All right, and we're down to that group. I did want to show you, by the way, I forgot that I did this. One of the ranges of motion this robot shoulder has is to rotate around this pillow block bearing using these hydraulic cylinders. And so the robot arm has been rotated in a little bit around this axis compared to the standard normal position. But we've got the arm at the place of abduction. And a feature of SketchUp is, this is why I have these little marks here. They're in the center of this shaft. And if you want to do motion with particularly rotary motion in SketchUp, it will automatically put the rotary motion on the plane of this surface. So there's motion, and so you see we put it there, and we can force it to use that. And so now another thing that SketchUp does is you can say, okay, I'm going to move it, but I need to come back out here and look at what's going on. And SketchUp lets you do that. It lets you have motion available, but it lets you look around. And the amount of movement I want to do is 60 degrees. So I can type in 60 and it will move it. So that's 60 degrees. And there is the 60 degrees that we've rotated it, and it has got the clock out, which means I'm out of time. So we will close this out, and then we'll come back into the robot when it's in this exact condition, and I'll show you what we're going to do next.